speaker, Geoffrey Penington from UC Berkeley. And as you may know, he's one of the leading researchers in the subject which bridges between quantum information theory and quantum gravity. And Geoffrey Penington received his PhD from Stanford University 2020, and the same year he joined UC Berkeley as a faculty member. And he has written many outstanding papers which apply the idea of quantum information theory to quantum gravity. And especially one of his famous papers is the discovery of so-called island formula, which computes this entanglement entropy in evaporating black hole, and which is a key to understand the information problem of black holes. And now we'd like to invite Geoff Penington to start his colloquium. The title of his talk is What's Inside a Black Hole? Please start.
Okay, thank you so much, Tadashi, for that very kind introduction. So yeah, this talk is obviously about black holes, hence the title. But I wanted to start with something a bit more down to earth, namely an egg. So we're going to take this egg and we're going to drop it, and it's going to hit the ground and it's going to explode outwards and break. And then we're going to stop time. We're going to reverse the velocity of every single particle. We're going to go one by one and we're going to turn them around so that they're now sort of splattering inwards rather than outwards. And then we're going to start time again. And while we did step 2, we probably also turned all matter into antimatter and did a reflection of the universe. So it's a full CPT symmetry, but never mind. So what's going to happen? So the answer is that the egg is going to splatter together. It's going to splatter together in exactly the right way that it perfectly solidly forms into a whole egg, while giving that whole egg some momentum upwards so that it pops up into the air. So at the very fundamental level, the laws of physics, as we know and understand them, are reversible. The same laws describe revolving time forwards as revolving time backwards, up to those subtleties I mentioned about particles versus antiparticles and so on. But in particular, that means that information in physics can never be truly destroyed. So if I have some book, and for some reason I want to destroy that book, then maybe in practice I would do something like take it to a shredder and feed the book page by page into the shredding machine. And in practice, this of course means that nobody will know what the book was, unless the NSA or some major global intelligence agency decided that the thing they most wanted to do in the world was work out what I'd been reading. And if they do want to do that, they could painstakingly piece together all the tiny little pieces very carefully, match up the microscopic structure of each little bit, put it back together. So the information in the book is still there. It's just harder to read than it was before. Okay, well, maybe then I step my game up, and rather than just shredding this book, then I burn it in a fire until there is nothing left but ash. So in that case, I think it's safe to say even the NSA is not going to be able to unburn the book. For all practical purposes, information has been destroyed. However, in principle, the laws of physics still say that it's true that the information in the book is encoded in the states of the air molecules, the light and the heat emitted, the ash that got left behind, and so on. Essentially, this is the statement that quantum mechanics is unitary. Okay, let's really step our game up once more. Now I'm going to take this book, I'm going to get a spaceship, I'm going to fly however many light years I need to find some nice convenient black hole, and I'm going to throw that book into the black hole. So Hawking in the 1970s made an extraordinary claim about this process, namely that if we do this and then we wait long enough, then the information that was in the book will genuinely vanish from the universe. That combining quantum mechanics and gravity together gives a theory that is fundamentally irreversible in a way that no other theory of physics is. This is the famous black hole information problem. So the goal for this talk is a fewfold. The first is to try and explain at a high level why Hawking made such a radical claim. Why did he believe information was lost? In very brief summary, it's because of the black hole, if you leave it, turns out to evaporate. It's not actually black, it's just dark gray. And it seems like the radiation that it emits forgets about the state of the matter fell in. Second is why most people now think he's wrong. And this is going to come down to these papers that Tadashi mentioned at the beginning of the talk, where in 2019, for the first time, we finally had direct gravitational calculations that showed information coming out in the radiation after all. And then finally, I'm going to try to talk a bit about something more recent, which has to do with the question of what actually happens if you jump into a black hole, what do you see inside, and whether black holes actually have an interior, as you would expect from classical general relativity, or alternatively, whether space-time ends at some firewall at the horizon, as been proposed in the last 10 years or so. Okay, but we're going to start way back in the 1970s, very high-level overview of why black holes behave like thermodynamic objects and the connection between black holes and this egg I showed at the beginning of the talk. So why don't eggs unbreak? Well, it's for the simple reason that to make that process happen that I showed, have it actually happen, not just take a video and reverse it, then we need to reverse the velocity of every single particle splattering away from the egg. If we just roughly reverse the velocity of most of the particles, then the egg will splatter back together, but it won't reform into a solid object. It will just form a mess that then splatters on the floor again. Essentially, this is the statement that there are far more states that look like a broken egg that are macroscopically indistinguishable from the true one that formed than there are states of an unbroken egg. And when we evolve backwards in time, each of those macroscopically individual states has to come from a different initial condition. Because there just aren't very many, by comparison, states of an unbroken egg, only a tiny fraction of the broken egg states can reform into an unbroken egg. So it's a very unlikely process. And the way we capture this, of course, is this statement that the entropy of the broken egg is larger than the entropy of the unbroken egg, and it is very unlikely for entropy to decrease by macroscopic analysis. That's the second law of thermodynamics. Okay, so what does this have to do with black holes? Well, the dynamics of black holes also turn out to be irreversible. So this is a simulation of two black holes orbiting each other and then merging into one. And there's a general statement that this can never happen in reverse. So black holes can merge together, but they can never unmerge. A black hole can't spontaneously emit out a smaller black hole. In fact, there's a precise statement that's sort of the black hole analog of this second law, which is the Hawking area theorem, that if we add up the total areas of the event horizons at the edge of all of these different black holes, then it always increases over time. So this looks very like the statement that entropy always increases. Okay, that's just saying there's something that monotonically increases over time. That's not very deep or interesting. But it turns out all the other laws of thermodynamics also have analogs that you can think of as black hole thermodynamics. So we just described the second law of ordinary thermodynamics is that entropy increases, and for black hole thermodynamics, it's the area increases. Similarly, the zeroth law of thermodynamics says that temperature is constant in equilibrium, the system in equilibrium. And there's an analog for black holes that is this thing called kappa, called the surface gravity of the horizon. The black hole is constant everywhere on an equilibrium black hole. First law of thermodynamics is really that energy is conserved, and that's also true for black holes. But there's a closely related statement that is less obviously related to something about black holes, which is that the so-called Clausius relation, that for an adiabatic process, then the change of energy is equal to the temperature times the change in entropy. And again, there's an analog for black holes that sort of replaces temperature by something proportional to kappa and replaces entropy by something proportional to this horizon area. And in this case, we have a constant proportionality that's 1 over 8 pi g Newton. Finally, Third law of thermodynamics says that there's no process taking a finite number of steps that ever reach absolute zero, T equals 0. And similarly, for black hole thermodynamics, you can never get to surface gravity 0, which is called an extremal black hole in a finite number of steps. So the analog, seemingly, is that any law of thermodynamics, you should just replace temperature with something proportional to surface gravity, entropy with something proportional to horizon area. You can't quite fix the constant of proportionality because if I multiply the analog of temperature by 2 and divide the analog of entropy by 2, then all the laws of thermodynamics are unchanged. There's some relative scales there that are not fixed by any of these laws, and so it's not quite obvious how they're related. Now, these black hole thermodynamics laws were first figured out in the 1970s. And when that happened, Jacob Bekenstein, who was a graduate student, I think, at the time, or maybe a postdoc, but as you can see from this one picture I found of him online, was preternaturally mature for his age. He made the radical claim that these laws of black hole thermodynamics are actually really just thermodynamics itself applied to the black hole system. A number of other people immediately replied by saying that was ridiculous, most famously Stephen Hawking. They were completely skeptical about this idea, and they were skeptical for frankly very good reason. There's two very good reasons, really. One is that if you have an entropy, as I already said, you need to have a lot of microstates, and black holes didn't seem to have any microstates at all. In fact, from the outside, they settled down to some unique fixed state. This was called the no-hair theorem. And the second that is if you have an object with non-zero temperature that can absorb light and can absorb stuff coming in from outside, then it also needs to radiate. It needs to radiate at that temperature. So black holes should glow if they have a non-zero temperature. But of course, famously, black holes are black and so do not glow. Unfortunately, or fortunately for Stephen Hawking, 3 years later, he made his greatest contribution to physics and showed that actually, if you add quantum mechanics, then black holes do radiate after all, they're not black. So how did Hawking do that? How did he come up with this argument? Well, the key ingredient is, in fact, quantum entanglement. So as we all know, quantum mechanics is weird. And one way that it's weird, probably the most important way that it's weird, is that if you have a system in quantum mechanics that's built out of two or more constituent subsystems, then classically you would be able to describe the state of the whole system by one describing the state of each individual subsystem. But in quantum mechanics, you can't do that. It's called quantum entanglement. And the point is that even if you know the state of the whole system perfectly, the best way you may be able to describe a subsystem is in some fundamentally noisy, uncertain way. So it has to be described by density matrix, this sort of quantum version of a probability distribution. We can quantify this uncertainty. We can quantify the amount of noise induced by entanglement between the subsystem and other system by this quantity called the entanglement entropy. It's just take the trace of the density matrix times the log of the density matrix. Should be clear, but I do want to emphasize that entanglement entropy is a very different concept to the entropy appearing in the second law. Both of them are quantifying noise or uncertainty. That's sort of what entropy is. But the second law, entropy, is quantifying uncertainty in the true state of the system because you are only aware of the macroscopic structure of the state. So it's a statement about your lack of knowledge of the true microscopic state of the system. Entanglement entropy is about a fundamental lack of knowledge that the true state is not even well defined, that because it's entangled with some other system, that the best you can do, even if you know everything about the state, still has some noise. So the two are related. The second law entropy is always bigger than or equal to the entanglement entropy, but they're not the same. And the final fact we're going to need later in this talk is that if you have a global state that is built out of two subsystems, and the global state is not noisy, it's pure, it's described by some state vector psi, then each of the two subsystems needs to have the same entanglement entropy. Okay, it's an easy result to prove. Okay, so the second ingredient we're going to need to understand Hawking radiation is quantum field theory. So empty space all around us is full of quantum fields. There are electric fields, magnetic fields, but also other fields associated with every fundamental particle, the electron field, and so on. And even in the vacuum of empty space, the state of fields at nearby points in space are entangled with one. So you can't talk about the state of the electric field at some specific point because that state is inherently noisy, it's inherently entangled with the electric field at every other point. In particular, one point in space that locally just looks like the vacuum is the event horizon of the black hole. So that means that fields that are just slightly outside a black hole horizon will be entangled with fields that are slightly inside. So it has nothing to do with the fact that it's a black hole, it's just a statement about quantum fields anywhere in the universe, and this is just one place where it's true. But now the interesting thing about a black hole horizon, of course, is that something inside it cannot get out. So these fields that start just inside and outside the black hole horizon, when we let them evolve with time, then fields outside can propagate off to infinity as sort of light or gravitational waves or whatever it might be. But the fields that are inside are stuck forever inside the black hole until they hit the singularity at its center. So this short-range entanglement that is present throughout space between things just inside and outside gets stretched halfway across the universe and becomes entanglement, long-range entanglement between fields going off to infinity and things inside the black hole. So that is not present in the vacuum. So it tells us that actually far away from the black hole, then these sort of waves traveling through space are not just in the vacuum state. They have to be excited in some way. And in fact, if you do the calculation, what you see is that they look like noisy thermal radiation. So they just look like completely random noise at some fixed temperature, carrying energy off away from the black hole. If you do the calculation properly, as Hawking did, you can compute exactly the temperature of the black hole that this gives. And I think even just looking at this formula, you can see just how remarkable a contribution to physics this was, because it's really arguably the first great formula that combines in one formula all the major fields of physics together. So there's a speed of light here, so this is obviously a relativistic effect. There's a Newton's constant, so gravitational physics is getting involved. There's an h-bar, so it's quantum mechanical. There's a Boltzmann's constant, so thermodynamics is getting involved. And of course, there's a pi, so circles are getting involved as well. Okay, so if we learn this temperature, we know now that the temperature of the black hole, then we sort of can use this analogy of the laws of thermodynamics. We knew what the entropy was up to a constant, and we knew what the temperature was up to the same constant. So that temperature fixes the constant. And then we find out that the entropy of a black hole is not just proportional to the area of the horizon, but to be precise, it's the area of the horizon divided by 4 times some fundamental constants, including Newton's constant. So this is the so-called Bekenstein-Hawking entropy of the black hole. And if we believe that Bekenstein was right after all, certainly looks a lot more compelling now that we've found black holes have a non-zero temperature, then we should expect that, like any thermodynamic entropy, this should be counting the log of the number of states that the black hole can be in. Okay, but the important takeaways for us about this calculation is that this radiation going off to infinity feels completely random. It's as random as it can be while having a certain temperature. And in particular, it doesn't care at all, carries no information about the matter that formed the black hole in the first place. So on this diagram, the matter that fell into the black hole would be down here. It's space-like separated from this entanglement near the horizon that then got pulled apart to form the Hawking radiation. So that whole process just doesn't care about the matter at all. Okay, that's fine. That's not an information problem, because even though the Hawking radiation is noisy, it's just a subsystem of our full system. And in quantum mechanics, subsystems are allowed to be noisy if they're entangled. And it's entangled with the black hole. And so the whole global state of the universe of radiation plus black hole can still be noiseless, can still be a pure state. We just have to have this entanglement between the radiation and the black hole. However, the longer we wait, the more radiation the black hole emits. It just keeps radiating out thermally. And so we get more and more of these thermal degrees of freedom far away from the black hole. And moreover, each of them's carrying energy away, so the black hole has to be getting smaller. So eventually, if we wait long enough, we end up with some huge amount of radiation that's all escaped and all seemingly looks totally random, and a comparatively small black hole that's maybe a bit less than half the size it started with. And at around that time, seemingly the entanglement entropy of this radiation, the amount of noise that is supposed to be purified by the black hole, becomes bigger than this formula of the horizon area of a 4G that is supposed to count all the different states that the black hole can be in. Now, this is where this fact that if I have two systems entangled with each other and the global state is noiseless, the two systems have to have the same entropy comes in. So this is just impossible if the global state of the system is supposed to be pure, it's supposed to not carry any noise, because the entanglement entropy of the radiation needs to equal the entanglement entropy of the black hole, and that in turn needs to be less than the thermodynamic entropy of the black hole. So at this point, we really do have a paradox, and there's only two ways out. The first is that this sort of normal principle of quantum mechanics, that quantum evolution is described by some noiseless unitary matrix, has to be wrong. And information is just truly lost forever from the universe. That was Hawking's answer. Or alternatively, somehow Hawking's calculation that showed this huge thermal entanglement entropy for the radiation has to go wrong. And it has to go wrong around the time the black hole, by the time the black hole is essentially half evaporated. Can't just go wrong very, very near the end. Okay, so this was sort of the status of things for several decades after Hawking's calculation. So we're now going to jump forward to 2019 and start talking about more recent developments. And the idea, in retrospect, what we should have been thinking was quite simple. It's just, how do we test to tell if information has actually been lost? What is an operational thing we can measure that will tell us once for all? What, we can't really do an experiment, but what's the thought experiment we can do that will tell us whether Hawking is right or not? So there's a lot of processes out there that look random, but are actually not random at all. They create the illusion of randomness. They're what's called pseudo-random processes. So one example is one of these Galton boards where you drop a ball in, and then it bounces around, and then it ends up in some location. More generally, just any sort of chaotic classical system, its behavior at long times will just look random. Random number generators in a computer, right, appear to be random, but they're actually computed by some deterministic process. And of course, even the breaking egg I showed at the start of this presentation looks a very, very random process, but actually it's completely determined by the initial conditions. So let's say we have some algorithm that claims to be random. Let's make it as simple as possible. Let's just say it's some algorithm that just spits out a number on a computer screen that claims to be evenly distributed between 1 and 100. How would we tell whether that process was actually truly random or not? Okay, so we can press go, and we can see what comes up, and the number that comes up on the screen is, let's say, 7. Does that tell us whether it's random or not? Well, not really, right? Because any number would have been equally likely if it was random. And if it's not random, it's actually deterministic. Who knows what it's meant to put out? So unless we have some reason to think it's secretly always going to produce 7, then this doesn't tell us anything. But now let's get 2 copies of the system. Let's make sure we initialize them in exactly identical conditions, have them perfectly identical. Of course, in practice, that's hard to do, but in a thought experiment, it's easy. And then we run it on both of them at the same time. And let's say we both of them give 7. Well, that's starting to look a little sus, as the kids these days would say. Right, we're maybe starting to think that actually this isn't random after all, because if it was truly random, the probability they would both be the same is the sum over all the probability squared, which in this case is 1 over 100. 1 over 100 chance both numbers are the same. But if it's pseudo-random and it's secretly some deterministic thing based on digits of pi and the time of day or who knows what, then it would always be exactly the same as long as the conditions are identical. And so the probability this happens is 1. So if we're good Bayesians, we should think of this as strong evidence that this isn't actually random. Okay. So there's a quantum version of testing to see whether 2 states are the same that's used in quantum information theory. It's called the swap test. And the idea is very simple. You just consider the quantum mechanical operator that takes 2 systems and just swaps them over. So this is some Hermitian operator. So it describes some measurement that you can do. And the expectation value of it is given by the trace of the density matrix for that system squared. So in this case, we're going to consider taking the radiation here and swapping it with the radiation here. And the expectation of that should give us the trace of the density matrix squared. So if the radiation was, say, in a completely pure state, then this would give 1, because the density matrix would just be a projector. The trace of a projector squared is 1. But if it's some highly entangled, highly mixed state, then we'll get some answer that's much, much smaller than 1, that becomes very close to 0. Okay, so this is an actual thing you could do as an experiment to just test how noisy or not your state is without having to know what the state is, without having to know exact description of it. Okay, so let's do that. So we take our radiation on one copy of a black hole and we swap it with radiation on another copy of a black hole. So that's what I just did. And you'll see that the state looks pretty different from before. So previously, the interior of this black hole was entangled with the radiation of the same black hole. But now the same interior is entangled with this other copy of the radiation over on the right-hand side. So seemingly, we get some answer that this state after swapping is very close to orthogonal to the state before swapping. So the expectation value seems to be very small. And in fact, if you do the calculation carefully, then you get the expected answer for random thermal radiation. You get the answer Hawking would have gotten. It's all boring. It's just the same thing Hawking was seeing. But that's a bit too quick, because when we did that, we assumed that these spacetimes involving the black holes were totally fixed. And we don't live in a universe where the spacetime is fixed. We live in a universe where the spacetime is dynamical. And more than that, it should be a spacetime that is quantum mechanical, because it's dynamically coupled to quantum systems. So we need to be doing a calculation in quantum gravity. And if you're doing quantum mechanics, then when you do any computation in a path integral point of view, you have to integrate over all possible dynamics of your dynamical degrees of freedom, regardless of whether they're sort of allowed classical dynamics or not. You're allowed totally crazy quantum fluctuations in this path integral, and you just have to add them all up. So one thing that can happen in quantum gravity, the dynamical degrees of freedom are just the space-time geometry. So we allow the space-time geometry to do crazy stuff. And one thing that it can do is to have a so-called space-time wormhole form, whose effect is to basically dynamically swap this left black hole interior to this right-hand black hole interior. So the way the space-time is glued together, something that was over here then gets detached and glued instead to this exterior over here. So this is some crazy, wacky process that is highly suppressed. It's like some instanton process happening in a field theory or something that has tiny, exponentially small probability of happening, but it can happen. And if it happens, then you'll notice that now our state, after both we swap the radiation and this crazy dynamical space-time wormhole randomly swap the interiors, looks pretty much like the state we started with. So if this wormhole happens to form, then we end up with the swap just taking of the radiation, just taking us back to the original state. And so we get that the expectation value would be 1 if the wormhole forms. Turns out that exactly after the page time, so exactly at the point where Hawking's calculation seemed to give nonsense, then the probability of a wormhole forming becomes bigger than the answer, the sort of classical space-time answer where nothing weird happens, and starts to dominate the expectation value of the swap operator. And in fact, the probability this wormhole forms is directly related to e to the minus the area of the horizon over 4g. That just follows from the action that you have in quantum gravity, the Einstein-Hilbert action. And so this gives an answer for the expectation value of the swap operator that is exactly 1 over the number of states the black hole can be in. But that's also exactly the smallest answer we can get for the expectation of the swap operator without having a paradox. If the entanglement entropy of the noisiness of the radiation has to be equal to the noisiness of the black hole, the entropy of the black hole, which in turn has to be less than the log of the number of states of the black hole, this is exactly what we get if the black hole is just in a totally random state, and then the radiation is purifying that random state. In particular, what you'll see is that as the black hole evaporates, the area of the horizon gets smaller. That means this exponential gets bigger. It's corresponding to the black hole having fewer states it can be in. And so the radiation starts getting less noisy over time. So the radiation gets noisier and noisier, more total noise. And then exactly when that would be paradoxical, would mean information was lost, the noisiness starts going down until in principle, if the black hole completely evaporated, you'd get that it's 0 and no information has been lost. Okay, so that calculation is great, but there's a couple of problems with it. One, it was a little bit heuristic, as I said it so far. And also, this quantity trace of rho squared, it's a decent measure of how noisy things are. It's related to something called the Rainey entropy, if you know that. But the much better measure is the entanglement entropy that I talked about earlier. So that's what we'd really like to compute is the entanglement entropy of the radiation. So that's the first problem, is we're not really computing the things we want to be computing. The second problem is that unless we're in a very simple toy model, then this space-time wormhole that swaps the two interiors, we don't know the explicit semi-classical solution that gives it. So we are very confident there should exist some saddle point, Euclidean saddle point, that describes this wormhole, but we don't have explicit examples in something like our universe with 3+1 dimensions and lots of fields and so on. The reason for this is, in fact, that this trace of rho squared quantity is not a very good measure. It's a bit of a weird measure of the noisiness of the radiation. In particular, it gets dominated by some tiny exponentially small probability that just lots of radiation gets emitted really fast, that the radiation happens to have a lot of energy, and so the black hole gets very small. So the better measure is the entanglement entropy. So how would we go about computing that? By some sort of similar calculation? Well, the entanglement entropy, rather than trace of rho to some power, is trace of rho log rho. But we can write that just as a limit as n goes to 1 over 1 minus n times log of trace rho to the n. And then we can just do the computation of trace rho to the n for integer n. This is something called the replica trick. Get an answer for each integer value of n, and then try to analytically continue that answer to non-integer values and eventually to the limit n goes to 1. So for integer n greater than 1, then the dominant contribution after the page time to this trace of rho to the n looks like a multi-boundary space-time wormhole. So it's very closely related to the space-time wormhole we just saw for n equals 2. But for general n, what happens is that this thing is the expectation value of the swap-like operator, where we swap the radiation in copy 1 into copy 2, we swap the radiation of copy 2 into copy 3, and so on round in some big circle. And then the dominant contribution comes from quantum gravity dynamically swapping around all the interiors in the same circle. So there's one big space-time wormhole that glues interior 1 onto exterior 2, interior 2 gets glued onto exterior 3, and so on. Okay, this is some topology of space-time that can happen. You can argue that this is the one that dominates. Okay, so then we can do some very clever trick. We say, okay, there's n of these black holes here, but they all look the same, right? In fact, there's some symmetry where we sort of spin these four, permute these four black holes around. So we move this one to here, this one to here, this one to here, this one to here. And the whole geometry, including the space-time wormholes, will look the same. So that means that we can just quotient by that symmetry, and all the data is contained in looking at what happens to just one of these black holes. If we're just looking at one of these black holes, then there's no reason n needs to be an integer, and we can sort of analytically continue the answer to non-integer n. So this was first done in a slightly different context in a beautiful paper by Lukovitz and Maldacena in 2013. In our case, what happens then is we analytically continue to non-integer n, and in the limit n goes to 1, then it's basically like no swapping is happening at all, and we just have the one ordinary black hole emitting its radiation with nothing weird going on at all. Except there's a relic there. There's a relic there of the fact that there was a wormhole for n greater than 1, which is that we need to keep track of which part of the space-time, which part of the interior got swapped through the wormhole. Okay, so the part that got swapped wouldn't dynamically get swapped if we try to do one of these swap tests or the replica trick. Now, it turns out you can compute exactly what region that will be. It's something called the island. So this is what Tadashi mentioned. So what happens is that when you impose the semi-classical Einstein's equations in the limit as n goes to 1, you find that the region that's swapped has to be bounded by something called a quantum extremal surface. So this is a quantum generalization of something originally introduced by Tadashi in first in a paper with Ryu, and then one by Hubani and Rangamani. So what it is it's a surface where if you move this surface a little bit, if you move this yellow dot a tiny bit, then the combined quantity of the area of that surface plus the entropy of everything inside the surface and all the radiation stays constant. So it's sort of a fixed point of this formula. This formula is called generalized entropy. And you can show that the Einstein's equations tell you that perturbing this yellow dot has to leave this quantity fixed, right? So that it depends, it's the area of the yellow dot, which is a two-dimensional surface, plus the entropy of all this stuff. Then you move the surface a little bit. In general, that quantity would change, but you can find some surface where it stays constant. And this is called the quantum extremal surface. And it turns out that even though we couldn't work out, say, for n equals 2, exactly what a wormhole looks like in realistic black holes, we can, at n equals 1, compute where this surface will be. And that's what we need to compute the entropy, the entanglement entropy of the radiation, which is actually a much better quantity than trace of rho squared. So we failed at something and instead got something better and more useful. So really, there's sort of two ways that we can have this surface this generalized entropy be constant if we perturb the edge of this part of the spacetime, the island that gets swapped through the wormhole. One of them is sort of trivial. It's just if there's no part of the spacetime that gets swapped through a wormhole, i.e. no wormhole exists. So that's the first option that sort of satisfies Einstein's equation. It's just that there's no island at all, and there's no wormholes, there's nothing weird, everything's normal. The second one is this special surface called the island QES that sits very close to the horizon of the black hole. When you work through all the details of the entanglement entropy being this analytic continuation of trace rho to the n, then you find that the entanglement entropy is given by first looking for all these extremal surfaces, taking each of their generalized entropy, and then taking the minimal generalized entropy out of that set. So in our case, we have to minimize over either having an empty island and just looking at the generalized entropy of that, or looking at the generalized entropy of this island QES. The generalized entropy of the empty island, well, the area of the edge of an empty region is 0, so this term is 0. And the Q of T entanglement entropy of the island plus the radiation is just the Q of T entanglement entropy of the radiation. So it's in fact just Hawking's answer. So when the QES is empty, then Hawking was right. And we get an answer that just looks like the thermal entropy of the radiation. But the generalized entropy of the island QES is very different. So its area is much bigger. Its area is roughly the horizon area of the black hole. So this first term gives a horizon over 4G. But this Q of T entanglement entropy is much smaller. It's much smaller because this thermal entropy of this radiation is purified by the stuff still inside the black hole, which is sitting in the island. So it's like computing the entropy of the whole global pure state rather than just one of the two subsystems. That's basically 0. In reality, it won't be quite 0, but it'll be very small. So this first term basically dominates. And if the island QES is the right answer, then we get the horizon area of the black hole. So our final answer for the entropy of the black hole is that it's whichever entropy of the radiation is whichever is smaller out of the thermal entanglement entropy that Hawking thought the answer was, and the area of the horizon divided by 4G. But that second term is exactly what we need to avoid any information paradox, to not have information be lost. It's saying Hawking's right, unless Hawking's answer would be paradoxical, in which case there's another answer which is just small enough to avoid a paradox. Okay, so that was the exciting punchline of 2019. We suddenly had a calculation that rather than saying the entropy of the radiation just kept going up until it became paradoxical, instead kept going up until it was about to be paradoxical and then started going back down. So the last part of this talk is going to be a bit more speculative, a bit more questionable, which is try to answer the question about what happens if you jump in and what's actually inside a black hole. So if we want to really solve the information problem, then it's not enough for the entropy of the radiation to start going down. What we also need to have is that the radiation needs to start carrying information about matter that fell into the black hole. If this doesn't happen, then you'll have the evolution will be noiseless, but it won't be sort of one-to-one. It won't be unitary. It will map lots of different initial states with different matter configurations to the same final state. Turns out that this can be done using similar wormhole calculations to the ones we used earlier. The trick is actually to use some explicit way of doing quantum error correction called the PETS map, and just try to use it to recover the information from this radiation. So there's something in the island that we want to recover, and we can try to use a quantum error correction algorithm to try to do that. And it turns out that algorithm will basically work if the thing we're trying to recover is inside an island, and if it's not in an island, then we won't be able to recover it. So if we're before the page time when Hawking was right, then this algorithm will just always fail because there is no island. And so the radiation generally carries no information that's useful for learning about the matter that fell in. But after the black hole page time, that's no longer true. We have this giant island, and anything in here is secretly also encoded in this radiation that's come out. So let's say we chuck something into the black hole after the page time. Conventionally, it's called a diary. Could be, for example, the copy of Twilight that I talked about at the beginning. So I've flown off to my black hole. I threw it in. Unfortunately for me, the black hole in question was already more than half evaporated. And the NSA had been secretly collecting all the radiation coming out after time, all that time. So then the question is whether I'm in trouble. Can the NSA figure out what I was reading? And initially they can't. So I've just thrown this diary in, and initially its world line will take it to the right outside of the island. It'll be to the future of the island. That means there's no way for me to pull it out through a wormhole and recover it using this algorithm. So I'm not able to, the NSA can't do any measurements on the radiation to learn what it was. But that's okay because the NSA are patient. And if they wait a bit longer, then more radiation will come out. And as more radiation comes out, then the definition of the island changes because the definition of the island depended on what radiation we're including. In fact, the island gets bigger. It sort of moves upwards and outwards. So now more of the black hole is inside the island. If we wait long enough, then this world line of the diary that fell in is now inside the island rather than outside. So this means that if I wait for a bit more radiation to escape, then somebody can actually learn what the diary was, can actually compute exactly how long you have to wait. It's given by this complicated formula that works out for only a few seconds for an astrophysical or even for a supermassive black hole. It's really pretty small timescales. And after you wait for that long, then you can do some very complicated measurement on the radiation. It's too complicated even for the NSA, but it in principle can be done that can teach you what was in the diary. So the information has fundamentally escaped. And this time of beta log SBH over 2 pi was famously predicted actually by my PhD advisor, Patrick Hayden and John Preskill back in 2007. They predicted it just based on the rules of ordinary quantum unitary dynamics and strongly coupled fast scrambling systems. We've now, in 2019, we were able to reproduce that calculation and that exact precise answer by doing a gravity calculation with a black hole. So that was obviously very exciting. But it's also, at the same time, somewhat problematic. It's problematic because in quantum mechanics, there's this famous no cloning theorem that says that quantum information cannot be copied. But now we've somehow concluded that this radiation out here is the same quantum information as this stuff that fell in. So how can that be true? How can that be sort of real? So there's some mathematical answer you can give, which is that these states of the black hole, where the diary is in different states, and we also have all the interior partners of the radiation, they all aren't actually quite orthogonal. They're all squeezed by quantum gravity into some Hilbert space whose dimension is e to the entropy of the black hole. So mathematically, we understand what's going on. And as long as you don't do any exponentially complex observable, you can prove that this can be consistent and there doesn't have to be a breakdown of the semi-classical calculations. But this still begs the question of if only SBH degrees of freedom describing this whole giant interior of the black hole are actually sort of real, if microscopically we only have this comparatively small Hilbert space that's supposed to secretly describe this much larger number of degrees of freedom, then do those degrees of freedom actually exist at all? Is the interior of the black hole real, or is it just some convenient mathematical fiction that lets you do calculations? So I don't think we know the answer to this question, and I'm not even really sure how we would get the answer. But the closest thing I think we can have to giving an answer was given in a paper about a year ago that I wrote with Raphael Busso. And the argument is basically that if you think the interior of the black hole shouldn't exist, then you should also believe some stuff outside the black hole shouldn't exist too. So the point is that because the island is normally behind a black hole horizon, the obvious way to test whether it's real would be to send some probe in and then get the probe back and ask whether that region of space-time existed or not. But this is impossible because if we'd have to jump in to determine whether it's real, if we don't want to die, if we want to stay outside the black hole, we can't ever test this because we can't get any probe back out. Even if we do thought experiments, even if we don't have to die because it's just a thought experiment, then the best ways we know to do thought experiments involve sort of using things like ADS-CFT, sending some probe in from infinity and then getting that probe back out so we can really do a well-defined calculation. And even in those thought experiments, therefore, we're really limited in what we can probe behind a horizon. Fortunately, it turns out that in certain weird circumstances, the island can actually extend outside the horizon. And in this paper with Raphael, what I showed is that it can even extend what we call the macroscopic proper distance outside. So the actual distance you can make it extend is roughly the square root of the Planck scale times the Schwarzschild radius of the black hole. The Planck scale is very small, so this still ends up being very small. For a supermassive black hole, it ends up being roughly an atomic scale. So this is very, very difficult to probe, of course, in practice, to get within the radius of an atom of a supermassive black hole and then get something back out. But we at least think that at those sort of scales, we understand the physics and nothing weird's going on. So how did we make this happen? How did we find these islands? Without going into huge detail, the trick was just to include Hawking radiation that never actually goes all the way out to infinity because it's not pointing quite the right direction. It has some angular momentum that means it ends up getting reflected back into the black hole. You can argue that this radiation could still be extracted, and so it makes sense to talk about its island. And when you compute its island, it turns out to get outside the black hole. Okay, so this has generally been a pretty theoretical talk, so I wanted to end on a plausible experimental note. So the argument is, let's say we wanted to experimentally determine what's inside the black hole without dying. Well, if islands outside the horizon are a real physical region of space-time that you can go into and outwards and so on, then I think it's reasonable to say that the interior should also be real too. The semi-classical interior predicted by general relativity should just be there. There's nothing more problematic about the interior than there is about these islands outside the horizon. So if you accept what you need to accept to get the former, you get the latter. Okay, so how do we then test the island outside the black hole? Well, all we have to do is fly to some nearby supermassive black hole. Technically, we should really wait until after the page time to really check for sure, but I think the experiment would be interesting regardless of whether we did this. Send a probe to within the radius of an atom of the horizon of that supermassive black hole, and then somehow get a signal back out. We talked in the paper a bit about how you could try to do this. It's pretty hard, but in theory, it can be done. And then if we get an answer that matches what's expected from semi-classical GR, we can be pretty confident that the interior is real, and what's inside the black hole is just a load of empty space until you hit the singularity. So, my understanding is that the way you get an experiment funded in the world is you make a very optimistic budget, and then in reality it costs way more than that. I think this is probably a very optimistic budget. So yeah, on that note, let me just say that if cost constraints mean we can't do this experiment quite as proposed, there is an alternative sort of cheaper option, It's not quite as good, but it would still be very interesting. You could imagine simulating the same experiment for a holographic black hole being simulated on a quantum computer. And maybe in 50 years or so, that will be something we can actually do. And it maybe won't tell us definitively what's inside a black hole, but it would be real, I think, experimental input. 50 years is maybe optimistic, but 100 years with some good AI, then I feel optimistic about it. Okay, so yeah, thanks guys very much. I can answer any questions and so on.
So thank you very much, really wonderful and very instructive talk. Thank you very much. So any questions or any comments, or if we have a question, please maybe just speak up. Sorry.
Hello.
Yes, please.
So I'd like to ask a question about this slide. And if result doesn't match semi-classical GR, what is the interpretation?
Yeah, so the obvious other option is that there would be some firewall sitting at the furthest out you can make an island, and then presumably anything you threw in, then just nothing would come back out. So if you tried to do some experiment like this and you saw nothing came back out, then either just your experiment broke, or probably there's just some end to semi-classical space-time, and you know, maybe something like a fuzzball, some physical object sitting at the location of this island, or further out, of course. Yeah, the black hole isn't a black hole, it's some highly quantum mechanical object. Yeah, the point is that if we can get inside that radius and still just see something that looks like empty space, then I think there's no reason to think that wouldn't still be true until we reach the singularity. There's no additional weirdness, no additional breakdown of principles that we're used to until you hit the singularity.
I see, thank you.
So can I ask a question? So
Yep.
in the end, you talk a very interesting aspect, like we can maybe detect this information recovery of black
Yep.
hole in real experiment, also maybe observation of the supermassive black hole. So
Yep.
this recovery map, as you mentioned, this PETS recovery map, and
So
that's supposed to be very highly complex.
yeah.
Because
I
it
should
looks
distinguish
difficult to
two
do it
things.
in a quantum computer and so on. But do you have any
Yep.
comment?
Yes, so there's two different things you could try to do. One is to show that to sort of recover information from the radiation that has fallen in. That is going to be very, very hard. The comparatively easy thing to do would be just do a swap test, but even that, unless you've let the black hole really completely evaporate, then you still need to do exponentially many times, because you get plus or minus 1 and you're trying to detect an expectation value that's exponentially small. So that's really, really hard. What I'm talking about is something comparatively simple, which is have something fly into the island and then just fly back out. And so you never do anything with the radiation. And in fact, the radiation mostly just falls back into the black hole. That's sort of why the island is able to get outside the horizon. But in principle, this island did exist and something would have gone into it and then back out. And so the fact that that happens tells you that there wasn't a firewall there, and therefore tells you that presumably there isn't a firewall inside the horizon either.
The information you need to deal with is limited. So you can...
Say that again?
I mean, you can measure a few qubits to detect that effect.
If you had a big enough black hole, like larger than supermassive black holes, you could imagine literally building a rocket, and there's subtleties. You need to be careful not to make the black hole bigger by firing your rocket, but let's not get, there's ways around that. And you could literally have it fly into that region and then just fly back out. You would just design a thing that could do that. And then it would have probed the island. It could be
And just only, measurement of a small amount of qubit is enough to detect.
Yeah, so good. So if we did it on a quantum computer, yeah. So the thing, okay, if in a simulation, probably what you want to do is somehow do some scattering experiment or something that probes very close to the horizon of the black hole and see the physics there being unchanged. So, you know, that could in principle be like some 4-point function or something. It's not non-perturbatively hard to. I'm not claiming it's easy, but you know, there are things you
I
could
see, I see. Yeah, I see. But much
like
easier.
you could make a
measure.
very charged black hole and then fire in some charged particle with really, really high energy, and then it would get very close, but then get repelled back out.
I see. Yeah, I see. It's more a particle physics like experiment.
Yeah.
Yes.
Yep.
Okay. I see. Very interesting. Thank you very much. Okay, so any other questions?
May I ask a quick question?
Please.
So I just want to make sure when you say you have a replica wormhole and then inside when you say, for example, n equal 2 for the purity calculation, when one enter into the so-called the island region, it's implicitly connected through the wormhole to the other replica. Is that right?
Yes.
Right.
When you do the swap, yes.
Right. And how should we interpret this physical process going to one law and then through the wormhole you go to the replica? I mean, physically, what is the physical interpretation?
Yeah, I mean, I think okay, it sort of depends on what you're imagining doing, right? If you just made two black holes and then you do a load of measurements on the radiation, then these are physical objects, and you could just imagine the space-time wormhole is just a physical thing that forms and swaps the interiors of the two black holes.
So you consider as if there's a two exactly same copy of the black hole formation.
You could imagine doing this experiment, right? At least on a holographic black hole in a quantum computer or something. But in principle, in the real world, you could just build two like microscopic black holes by colliding things together at Planck energies. And then you just make them both in exactly the same way, let them both evaporate, collect up the radiation, and then do a swap test on that radiation in some quantum computer. And then the space-time wormhole would just be some physical dynamical process that happens. The more mysterious question is, let's say you just somehow knew what the actual black hole S matrix was as like a mathematical formula without doing any experiments. Maybe we solved non-perturbative string theory or something and just somehow work it out. Then in principle, there's just some fixed algorithm that we could do that would decode the radiation, say, or and tell us about the diary that flew in.
Right.
In that case, it's very unclear what this PETS map calculation that involves space-time wormholes connecting the real black hole to some fictional black hole, like the physical interpretation of that.
Okay, but let me make sure one simple thing. When you prepare, say, two initial configurations, say the thermal gas, both of them gravitationally collapse to form a black hole. As initial condition, these two identical thermal gas, which should form the two identical black hole, do they have to be entangled a priori, or they can be totally independent?
No, totally independent.
Totally independent.
Yes.
So then once, say, A thermal gas collapses to form black hole, and then B identical one form a black hole. Through the mechanism, once you are enter into the black hole, through the A, you can go to the black hole B, secretly through the wormhole. Is that right? Is that what you say?
So the probability of the wormhole forming is exponentially small.
Yeah, I understand.
It's a tiny effect.
I understand. But even after the page time, suppose such a black hole is formed.
Even after the page time, it's still exponentially small.
But suppose they form exponentially small.
So then yes. I mean, it's like saying you can run at a wall and then quantum tunnel through that wall and
fine,
the other side. It's
still,
a possibly unlikely process, but yes, in principle,
good.
It can happen.
Good. I agree. But then my question is that even if it passes through the wormhole from A to B black hole, still
Yep.
behind the horizon. Is that right? Still behind the horizon.
Yes.
So how do you detect whether it come to B or not? Theoretically, I mean, not experimentally. Do you have any idea?
I
It's hard,
mean,
no?
you can't really.
You can, right?
You can detect it by seeing the entropy of the radiation go down. I guess you could do something like, you could jump into the other black hole
Yeah,
and see
okay.
if that
Okay,
thing is
okay,
there, but
okay. But it's not that simple.
sacrificing your life for an exponentially small probability of seeing something seems not really worth it.
So okay, good. So just to make sure, so this replica wormhole doesn't have to be regarded as early radiation, something like that. Is that right or not?
Doesn't have, could you say that again?
Doesn't have to be regarded as like early radiation.
No,
Say
no.
early radiation. No, it's totally independent state.
Yeah.
Okay, thank you.
西村さん Do you have a question?
Yes, thank you. I have a slightly more general question. So when ADS-CFT appeared, many people said that if you describe black hole evaporation in the language of gauge theory, it should be unitary. So there should be no paradox. So can you recast your nice interpretation in that language?
I mean, I guess what I would say is that is the boundary picture of what happens and how you know that it's unitary. This is a bulk picture that is showing the same thing. So it's the sort of other side. It's the gravitational description of the same process. Like we knew post ADS CFT that it's clear from the CFT that the information had to be preserved, but this is a way to do the calculation in the bulk that sees the same thing.
Yeah, that is quite a general statement, but
Yeah,
can you make the relationship more precise or concrete?
Not. I can't think of any more precise statement. Like, I don't think this calculation can see that. I mean, it can maybe see that the theory is holographic because it sees, say, the page curve, but I don't think it knows, for example, that the holographic dual is a gauge theory. So I don't think, I don't have a particularly good answer. I'm sorry.
Yeah. Okay. Yeah. Thank you very much.
Thanks.
Can I ask a question?
Yep.
I have a question regarding the island outside horizon.
Yep.
Is the island here? Is the entire island placed outside the horizon, or just island just extends outside the horizon, but still?
The latter. It's overwhelmingly inside the horizon. It just sticks out a little bit.
I see. Then, is it possible to? Is it always possible to reconstruct the interior information just by accessing the tiny bit of portion of island that is in the outside?
No. Like what the island tells you is that if you collect all the radiation and do something very complicated to all of the radiation, you can reconstruct anything within the island. But the fact that the island extends outside does not help you do that. It only extends a tiny bit outside. The actual stuff in the island, a tiny bit outside the horizon, is not directly useful to learn about stuff inside the horizon. What you want is the radiation.
Then what do you mean by this experimental proposal slide?
Good. The point is that there is one, I think, somewhat reasonable point of view you could take, which is that anything that's inside an island can't really exist because it's really just the radiation. And that you shouldn't have quantum cloning, and so it's some mathematical fiction that it's a way to describe the state of the radiation, but it's not actually like a real region of space-time. So then the point would be that if the island extends outside the horizon, you can just fly into it and then fly back out, and then if you get back out, then like it probably existed. I mean,
But
maybe
isn't
you
there?
didn't, and it just you came back out with memories of it, but that feels.
But like since the island lies not only just outside of the horizon, but also still extends interior of the
Yeah.
black
You're
hole.
not probing.
Yeah.
You're not checking that all of the island exists. You're checking that some of the island exists, right? But if the point is to have islands not exist so that you don't have these issues with apparent quantum cloning and so on, then you need all of the island to not exist. So all you have to do is check some part of it that is inside the island, and you will have shown that that's not true. Of course, it could be that the part of the island outside the horizon exists, but the rest doesn't. But it doesn't help to do that, right? Then you've already had to accept the weirdnesses of quantum cloning, of non-isometric codes, however you want to talk about these things, state dependence that comes with believing in a semi-classical of an interior of a black hole. But then you also have to believe that somehow a firewall magically forms at the horizon, even though we know no reason that would happen. So it's like the worst of both worlds. To believe that the island exists outside the horizon but not inside.
Sorry, I think my point is if the global unitary acting on the island, then like possibly the radiation you want to see from the island outside the horizon still get like really scrambled with the information in the island in the interior of black hole. So how did you know? How can you be sure that you can get a radiation just from the island outside the horizon?
I'm not quite clear on the question. I maybe. So here's what I'm imagining doing. This is maybe just restating stuff, but you have some island here. You have the black hole horizon. Okay, so there's a load of radiation out here, and this island is associated with that radiation. I'm not imagining doing anything to that radiation. It's just there. It's actually a lot of it's going to fall back into the black hole through here. It's going to get reflected. But right now it's just sitting way out here. And I'm going to take a rocket, and I'm going to have the rocket fly like this. And then I'm going to say, if the rocket came back out, then, it does some recordings or whatever during this little bit here. And then we tested whether this part of the island existed. So we didn't have to do anything to the radiation. Is that clear? Maybe I'm not sure I'm answering the question, but I'm not quite clear what the question is. So
I see. Not exactly sure, but maybe I should consider a little bit on my own.
Thanks.
Yeah, thank you.
Sorry, I wasn't more clarifying.
Okay, so any more questions?
May I ask some more basic questions? Could you go to slides on the island where you introduced island, and there are some formulas for entropy, generalized entropy. I want to know.
All right, I'm just going to stop sharing for 2 seconds and then.
Oh yes, now I see. Yeah, so on this slide there are two equalities. The third one may be just an approximation. So is this kind of conjecture or more solidly derived one?
Which both of everything on this slide, I would say is pretty solidly derived. There are some minor assumptions in the derivation that have only been shown in special cases. The main one is that the replica symmetry is not spontaneously broken in the bulk. We have a pretty good understanding of when that happens, and this is not a case where we'd expect it to happen. Like we're very confident it doesn't, but in like a universe like ours in 3+1 dimensions, then that's not sort of been checked. But modulo those minor assumptions, then this first equality is a derivation. It's essentially the Lukowitz-Martinsina derivation of the Ryutake-Nagi formula. And then this second equality is an approximate equality, but it again is derived. I mean, the first one is essentially exact. I mean, it's essentially Hawking's calculation. And the second one is derived. Yeah, it's true up to order 1 corrections.
I see. So maybe
these are both order S, and it's true up to order 1.
In lower dimensional theory, where the holography is available, using holography, you derive this entropy formula. Is it that?
This is derived. This entropy formula is derived in any dimension.
Oh, okay.
All of this is derived really in any dimension. There are these, certain assumptions about replica symmetry not being spontaneously broken and stuff that have only been shown in models where we can sort of do the calculation without that approximation, but they're true in those simple models. Those assumptions, we expect they'll still be true in any theory. Like we know why it can fail and it doesn't happen for radiation. Like it's a very solid assumption, but essentially the derivation has been done in any dimension, and yeah.
I see. Thank you.
Okay, so we had quite a lot of questions, and yeah, let us thank the great talk, Geoffrey.
Thanks a lot for inviting me.
Thank you very much.